Have you ever stared at a Cambridge Physics past paper and felt like you were just staring at completely random questions? Well, I want you to change your perspective right now. You see, there is no paper, only patterns. Once you learn to see the code behind every single question, you crack the exam reality. Welcome to The Explainer. I am your host, and I'm absolutely thrilled to have you here today for this masterclass on Cambridge IGCSE Physics, syllabus code 0625. If you are a focused learner looking to truly master your understanding of the physical world and dominate your exams, you are in the exact right place. Today, we are taking a deep, highly analytical look at a cornerstone of the syllabus, the dispersion of light, the mechanics of glass prisms, and the incredible visible spectrum. But listen, we aren't just going to decode how light behaves. More importantly, we are going to decode exactly how Cambridge examiners want you to think about it. I see two types of students fail this all the time. There's Alex, who overloads his answers with raw physics facts but provides zero actionable analysis. And then there's Sam, who rushes through the paper, completely missing the command word requirements and throwing away easy marks. By the end of this session, you are going to have the exact strategies to avoid being an Alex or a Sam. So, get ready to see the matrix of the mark scheme.
Okay, let's dive right into this. Here is our structured roadmap for today. Number 1, the 15% benchmark. Number 2, core principles. Number 3, the method mark strategy. Number 4, examiner warnings. And finally, number 5, evaluating exam evidence. Let's start with section 1, the 15% benchmark.
15%. That is the magic number. Did you know that mastering the dispersion of light, the visible spectrum, and monochromatic light accounts for approximately 15% of the total marks in your Cambridge 0625 physics examination? Think about that for a second. This isn't just a minor topic you can skim over the night before. It is a massive point score. The examiners are specifically targeting your ability to demonstrate a connected conceptual understanding here. Grasping this 15% can easily mean the difference between 1 or even 2 full grade boundaries. When a student like Sam rushes through a spectrum question and drops 4 marks because he didn't read the command word, he's literally throwing away a whole letter grade. Or when Alex writes a whole essay on the history of prisms instead of calculating the refractive index, he's losing out on that 15%. Mastering this specific chunk of the syllabus is absolutely critical to your overall physics success blueprint.
Let's move on to Section 2, Core Principles.
Before we can even begin to understand how light breaks apart into a rainbow, we have to understand light in its absolute purest, simplest form. Monochromatic light is defined strictly as light consisting of a single frequency and a single wavelength. Think of the word itself, right? Break it down. Mono meaning one, and chroma meaning color. One color. Now, if you take a pure monochromatic laser, let's say a strictly red laser pointer, and you shine it into a glass prism, it will refract, it will bend, but it absolutely will not separate into different colors. Why? Because there's only one frequency present to begin with. You can't separate what is already singular. Establishing this foundational definition is a mandatory first step before we introduce any complexity. When a question asks you to define monochromatic light, if you just say light of one color, you're going to lose the mark. The examiners want the rigorous scientific definition, single frequency and single wavelength. That is the code you need to write to get the mark.
But what happens when we use white light instead of that pure monochromatic light? Well, that is when we get dispersion. This is the separation of light into its constituent colors by a glass prism. Because white light is actually a chaotic mixture of many different frequencies, when it enters a denser medium like a glass prism, it slows down. But here is the critical, absolute, game-changing physics principle you need to understand. Different frequencies slow down by slightly different amounts. This differential slowing is the entire secret. It causes the light to bend or refract at totally different angles, physically fanning out the light into a beautiful visible spectrum. It's like cars hitting a patch of mud at different speeds. They're going to veer off at different angles. Now, before we continue and break down exactly how these colors arrange themselves, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the actual data behind this dispersion.
Now, what's really interesting about this slide is the hidden math behind the colors. Let's map the invisible mechanics of that dispersion across the 7 colors of the visible spectrum. Look at this data table. Notice the direct inverse mathematical relationship happening here. Red light has the lowest frequency, but it has the absolute highest wavelength, meaning it bends the least when passing through the glass prism. It just pushes right through with minimal deviation. But look at the completely opposite end of the spectrum. Violet light has the highest frequency and the lowest wavelength, so it gets slowed down the most and therefore bends the most. The examiners absolutely demand that you know this exact sequence, from red down to violet, and the precise inverse relationship between their frequencies and wavelengths. If you get a data extraction question, you usually have about 60 seconds to scan a chart like this and pull the core trend. The trend here is undeniable. As frequency increases down the spectrum, wavelength decreases, and the angle of refraction increases. But listen to me, memorizing that color table is essential, but it is not the final goal. I want you to read this direct quote pulled straight from the Cambridge Principal Examiner reports. Top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. What does that actually mean for you? It means rote memorization of the visible spectrum won't secure the top grades. You can't just be an Alex dumping memorized facts onto the page. If they give you a weird scenario about light passing through a diamond underwater, you can't panic. You need to understand the why well enough to apply the rules of refraction and frequency to that totally new, unfamiliar context. The assessment framework prioritizes analytical depth over superficial breadth. You have to see the underlying pattern, the code of the physics, no matter what weird scenario they dress it up in.
Let's transition to Section 3, the Method Mark Strategy.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into the strategy that actually gets you those top grades. We secure those marks by recognizing that examiners actively award points for your process, not just your final answer. This is the ultimate physics success blueprint. When you face a complex physics question on dispersion, you must follow this 5-step procedural framework. Step 1. Deconstruct the question. You have to decode the command words. Is it asking you to state, describe, or explain? Step 2. Extract relevant data from texts and tables. Step 3. Select your analytical framework. This is where you bring in the Peel framework: point, evidence, explanation, link. What physical laws apply here? Make your point, back it up with data from the question, explain the physics, and link it back to the context. Step 4. Execute your calculations or explanations with incredibly clear notation. And Step 5. Present your final answer using correct, highly specific scientific terminology. And this brilliantly illustrates why Step 5 is where so many students fumble. Putting your answer into practice requires strict presentation conventions. The examiners are specifically looking for proper headings in your tables. They want the correct scientific terminology. Remember, you never say light is bending, you say it is undergoing refraction. They want appropriate formats for your data, paying close attention to significant figures. And they demand clear, unambiguous annotations on your ray diagrams of prisms. Draw straight lines with a ruler and always draw the arrows indicating the direction of light. This all ties into the time management matrix. If you don't practice these conventions, you will waste precious minutes during the exam trying to fix messy diagrams. If you rush through the presentation like Sam does, you are literally leaving hard-earned marks on the table for no reason at all.
Section 4. Examiner Warnings. Pay close attention here. I am going to put my senior examiner hat on for a second. The crucial point of this whole explainer is helping you avoid these 3 critical traps that we see year after year. Mistake number 1 is the classic Sam trap, using the wrong analytical approach for a specific context because you rushed and didn't read the command word. If they ask for an explanation of dispersion and you just calculate an angle, 0 marks. Mistake number 2 is entirely unforced, forgetting to check your format, presentation, and significant figures. But mistake number 3, this is the ultimate grade killer. This is the Alex trap, providing a scientifically accurate answer that is completely disconnected from the context given in the question. You can write a totally true fact about the speed of light, but if the question was asking about a specific glass block, the examiner will just cross it out in red ink. You get no points for unprompted trivia.
To really hammer this home, compare these 2 approaches on screen. Imagine a split screen in your mind right now. We have a question asking why a specific blue laser behaves differently than a red laser in a fiber optic cable. The generic answer, the one that gets covered in red pen marks and loses marks, might just list the colors of the spectrum or vaguely say blue is different than red. It's totally generic. Now, let's transform that into a green checkmark answer using the PEL framework. The context-specific answer explicitly makes the point that blue light refracts more. It gives the evidence that blue has a higher frequency and shorter wavelength than red. It explains that this causes a greater change in speed when entering the dense medium of the optic core. And it links back to the specific refractive index inside that exact fiber optic scenario. Do you see the difference? The generic answer relies on rote memory. The context-specific answer decodes the matrix. You must always link every single point you make directly to the given scenario.
Finally, Section 5, Evaluating Exam Evidence.
Let's move to the highest cognitive domain required by the syllabus and see how this builds a master-level approach to physics. Higher-order assessment objectives demand that you evaluate the quality of evidence. You aren't just doing math, you are acting like a real scientist. When looking at experimental data about light dispersion, you must use this evaluative framework. First, limitations. You have to be able to identify flaws in how the data was collected. Was the light source truly monochromatic? Second, assumptions. You must question the premises made. Is the prism assumed to be in a perfect vacuum, or is air resistance and density playing a part? Third, alternatives. You must consider alternative interpretations of the data. And finally, conclusions. The Peel framework comes back here. You must be able to justify all of your final decisions with hard, specific evidence extracted from the text or graph provided. This is how you prove you don't just know physics, you can do physics.
Which leaves us with a final provocative question. Why do students find evaluating evidence and drawing conclusions so hard when faced with completely unfamiliar contexts? It is because they rely on fragile memory rather than a robust, structured analytical framework. When the context changes, memory fails. But a strong process? A process survives anything the examiner throws at you. Remember the 15% benchmark. Rely on your core principles, execute the method mark strategy, and heed those examiner warnings. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep learning, keep analyzing, and take care.